In 1971, two physicists loaded 4 atomic clocks onto commercial aircraft and flew them around the world. When the clocks landed, they disagreed with identical clocks that had stayed on the ground. Not because anything was wrong with them. They were working perfectly. Time itself had passed at different rates, depending on how fast the clocks had been moving and how high they had been flying. That experiment proved something most people still haven't absorbed. Space and time are not two separate things. They are one single fabric, and every time you move through space, you pay for it with time. Your motion through space literally slows your passage through time. This is not philosophy. This is not metaphor. This is measured, verified, and happening to you right now. And by the end of tonight, you're going to understand exactly why and exactly how we know. Before we go any further, if you find these kinds of deep explorations fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. For most of human history, the universe made sense, not in every detail, not in the movements of every planet or the cause of every storm, but in its deeper structure, in the bones of how reality was organized. Things were straightforward. Space was one thing, time was another, and the two had nothing to do with each other. Space was the stage, a vast, fixed, motionless container in which everything existed. Stars hung in it. Planets moved through it. You walked across it every time you left your front door. Space was just there, the same everywhere, stretching outward in every direction, providing an unchanging backdrop against which all events occurred. It didn't bend. It didn't shift. It didn't ripple or flex or respond to anything happening inside it. Space was simply the emptiness in which matter existed, and things happened. It had no properties of its own. It was passive, permanent, featureless, nothing more and nothing less than the arena of the universe. Time was the universal clock, a single, steady rhythm that ticked forward at the same rate for everyone and everything, everywhere, always. 1 second for you was 1 second for a person standing on the other side of the planet. 1 second on Earth was 1 second near Jupiter. 1 second at the edge of the solar system was 1 second in a galaxy 1 billion light years away. Time was absolute. It flowed forward at a constant and unstoppable pace, carrying the entire universe along with it. A clock in Tokyo, and a clock in London, and a clock drifting through the void of deep space, all ticked at exactly the same rate, because time itself was universal. It had nothing to do with where you were. It had nothing to do with how fast you were moving. It had nothing to do with space. Time just was. This picture of reality felt so obviously correct, so deeply aligned with everyday human experience, that questioning it seemed almost absurd. And the reason it felt so correct is that everything you have ever personally experienced in your entire life confirms it. When you walk across a room, the room does not change shape. The walls stay where they are. The floor remains flat. The distance from one side to the other is exactly the same whether you walk it quickly or slowly, whether you measure it in the morning or at midnight, whether you're moving north or south or standing on your head. Space is fixed. Distances are fixed. That seems self-evident, and at the speeds and scales of everyday human life, it genuinely is self-evident. No measurement you could ever make with your hands or your eyes, or the most precise ruler in your toolbox would show you otherwise. When you check the time on your phone and then call a friend across the world and ask what their clock reads, the two clocks agree. Your watch ticks once per second. Their watch ticks once per second. A clock on a wall, a timer at a racetrack, a stopwatch in your drawer, all of them measure seconds at the same rate. This is so obviously true that even pointing it out feels ridiculous. Of course, clocks agree. They're measuring time, and time flows at the same rate everywhere. That is simply what time does. Except it isn't. That deep, intuitive, seemingly unshakable certainty that time ticks at the same rate for everyone, everywhere, regardless of motion, is wrong. It is an assumption. It was a spectacularly successful assumption, one that held up for more than 2 centuries of the most rigorous science humanity has ever produced. But it was an assumption nonetheless, and it turned out to be wrong. The person most responsible for formalizing this old picture of reality, the picture where space is a fixed stage and time is a universal clock, was Isaac Newton. In 1687, Newton published his masterwork, the Principia, and in doing so changed human civilization permanently. His laws of motion and his law of universal gravitation explained how objects move, and why they move with a precision and a generality no one had achieved before. For the first time in history, a single mathematical framework could describe the fall of an apple from a tree and the orbit of the moon around Earth. The same equations that predicted the arc of a cannonball fired from a fortress wall also predicted the paths of the planets around the sun. Newton's physics worked. It worked so well and so consistently that for more than 200 years, no experiment contradicted it. Engineers used his equations to build bridges and calculate the trajectories of projectiles. Astronomers used them to predict the positions of planets decades in advance with extraordinary accuracy. When astronomers noticed that Uranus wasn't quite following the path Newton's equations predicted, they didn't question the equations. They didn't suspect the framework was flawed. Instead, they assumed there must be an unknown planet, one nobody had ever seen, whose gravity was tugging on Uranus and nudging it off course. They used Newton's equations to calculate exactly where that invisible planet should be. They predicted its mass. They predicted its orbit. And when they pointed their telescopes at that precise spot in the sky, there it was, Neptune. Discovered not by looking, but by calculating. Not by observation, but by trusting Newton's equations so completely that they bet a planet's existence on them. And won. That is how powerful Newton's framework was. But buried inside that framework were two assumptions so deep, so fundamental, that most people who use Newton's equations every day never even noticed they were there. Newton himself stated them plainly and then moved on as if they were self-evident truths, requiring no further discussion. The first was absolute space. Newton described space as something that remains always similar and immovable, without relation to anything external. Space is a fixed container. It doesn't move, it doesn't respond, it doesn't change, it simply exists, passively holding everything else. The second was absolute time. Newton described time as flowing equably, of its own nature, without relation to anything external. Time flows forward at the same steady rate, regardless of what happens in the universe. It has no connection to motion, no connection to matter, no connection to space. It is its own thing, an independent universal constant, ticking away identically for all observers in all places, under all conditions. These were not minor technical assumptions tucked away in a footnote. They were the foundation. Every equation Newton wrote, Every prediction his framework produced, every stunning success from calculating artillery trajectories to discovering new planets rested on the idea that space and time were separate, fixed, and absolute. Space was the unchanging stage. Time was the universal clock. Objects moved across the stage while the clock ticked identically for everyone. This was the architecture of reality. For 2 centuries and more, that architecture held. No cracks, no failures, no hints that anything was wrong. The equations worked, the predictions came true, and the universe behaved exactly the way Newton said it should. And then somebody noticed a crack. And it didn't come from where anyone expected. It didn't come from studying gravity or planetary orbits or the mechanics of falling objects. It came from studying something that seemed completely unrelated. It came from studying light. In the 1860s, a Scottish physicist named James Clerk Maxwell accomplished one of the most important unifications in the entire history of science. He brought electricity and magnetism together into a single theory. Before Maxwell, these seemed like related but fundamentally separate phenomena. Electric charges created electric fields, magnets created magnetic fields. The two interacted in certain situations, but they were studied by different people using different equations aimed at different goals. Maxwell showed they were not two things, they were one thing: electromagnetism. He wrote down a set of equations that described all known electric and magnetic phenomena in one clean, elegant mathematical framework. But when Maxwell worked through the mathematics of those equations, something unexpected fell out. The equations predicted waves, self-sustaining ripples of intertwined electric and magnetic energy that could propagate through the vacuum of space entirely on their own, without any wires, charges, or magnets to sustain them. And when Maxwell calculated the speed of these electromagnetic waves, using only the measured constants of electricity and magnetism, numbers that had been carefully determined in laboratories with batteries and coils and wires, the speed came out to roughly 300,000 kilometers per second. Maxwell recognized that number immediately. It was the measured speed of light. This was not a coincidence. Light, Maxwell realized, was an electromagnetic wave. It was a ripple in the electromagnetic field. The same fundamental kind of wave as what we now call radio waves or microwaves, just oscillating at a much higher frequency. One of the deepest mysteries in all of physics, the nature of light itself, was suddenly revealed as a consequence of electricity and magnetism working together. But hidden inside that triumph was a fuse. Maxwell's equations didn't just predict that light travels fast, they predicted a specific, fixed speed, and nothing in those equations suggested that this speed should depend on who was measuring it. There was no variable in the math for the observer's velocity, no adjustment for whether the light source was moving or the detector was moving. The equations simply produced a number, 300,000 kilometers per second, and that number was the same regardless of circumstances. Just a constant, clean and absolute and stubbornly fixed. At the time, this didn't seem like a crisis. Everyone assumed light was a wave, and waves need a medium. Sound waves travel through air. Ocean waves travel through water. Seismic waves travel through rock. Every known wave in the 1800s required some physical substance to ripple through. So electromagnetic waves, physicists reasoned, must travel through a substance too. They called this hypothetical medium the luminiferous ether. The ether was supposed to fill all of space, permeating everything, providing the invisible fabric through which light could propagate. And the 300,000 kilometers per second that Maxwell's equations predicted was simply the speed of light relative to this ether, just as the speed of sound is measured relative to the air carrying it. This fit neatly into Newton's picture. If the ether fills space and sits still, and light moves through it at a fixed speed, then your own motion through the ether should change the speed of light you observe. This is exactly how sound works. If you stand still and someone blows a horn, the sound reaches you at about 340 meters per second. But if you run toward the horn, the sound waves reach you slightly faster. If you run away, they reach you slightly slower. Your motion relative to the air changes the speed you measure. Simple arithmetic. The wave's speed plus or minus your speed gives the number your instruments report. The same logic should apply to light if the ether exists. Earth orbits the sun at about 30 kilometers per second. That is fast by everyday standards, but it is a tiny fraction of light's speed. Still, it should be measurable. As Earth moves through the ether in one direction during one part of its orbit, light traveling in the same direction should appear slightly slower from Earth's perspective. Light traveling in the opposite direction should appear slightly faster. 6 months later, when Earth has swung to the other side of its orbit and is moving the opposite way, the effect should reverse. The difference would be small, only a fraction of a percent of the speed of light, but late 19th century instruments were precise enough to detect it. In 1887, two American physicists named Albert Michelson and Edward Morley set out to measure exactly this effect. Their experiment, conducted in Cleveland, Ohio, was elegant and extraordinarily precise. They built an instrument called an interferometer. It split a single beam of light into two separate beams aimed at right angles to each other. Each beam traveled outward along its own path, bounced off a mirror at the far end, and returned to the starting point where the two beams recombined. If Earth was moving through the ether, one beam would be swimming partly with and partly against the ether current, and the other beam would be swimming across it. The two beams would experience slightly different effective speeds. When they recombined, they would be slightly out of step with each other, and this difference would produce a visible interference pattern, a telltale shift in how the light waves overlapped. Michelson's interferometer was the most sensitive optical instrument anyone had ever constructed. The entire apparatus sat on a massive stone slab, floating in a pool of mercury to isolate it from even the faintest vibration. The instrument could detect speed differences far smaller than what the ether theory predicted. Michelson and Morley rotated the apparatus to test different orientations. They measured at different times of day as Earth rotated beneath the stars. They repeated the experiment across different seasons as Earth moved to different positions in its orbit around the Sun. The result was nothing. Zero. No difference at all. No matter which direction they pointed the instrument, no matter what time of day or what season of the year, the speed of light came out exactly the same in every direction. There was no ether wind. There was no sign that Earth's motion through space affected the speed of light in any way whatsoever. Light did not behave like sound in air. Its speed appeared to be completely, stubbornly, inexplicably independent of how the observer was moving. This was one of the most important experimental results in the history of physics. Michelson and Morley had expected to find a difference and found none. Their experiment did not fail. It succeeded brilliantly at measuring something extraordinary. It measured that the speed of light does not depend on the motion of the observer, and that single, clean, undeniable experimental fact was flatly incompatible with Newton's absolute time and absolute space. Physicists struggled with this result for nearly 2 decades. Some proposed creative fixes. Hendrik Lorentz and George Fitzgerald independently suggested that objects moving through the ether might physically shrink along the direction of motion by exactly the right amount to cancel the expected effect. The math worked, but the explanation felt forced. It was like saying the evidence disappears because nature conspires to hide it. The fix preserved the ether, but at the cost of making it fundamentally undetectable, which raised the question of whether it existed at all. The real answer came in 1905 from a 26-year-old patent clerk working in Bern, Switzerland. His name was Albert Einstein, and his solution was not a patch, not a fix, not a clever workaround. It was a revolution. Einstein did not try to rescue the ether. He threw it away entirely. And with it, he threw away Newton's absolute space and Newton's absolute time. He replaced the entire foundation of physics with 2 postulates. Just 2 statements. The first was uncontroversial. The laws of physics are the same for all observers moving at constant velocity relative to one another. Newton himself would have agreed with this. If you're sealed inside a smoothly gliding train with the windows covered, no experiment you perform inside that train can tell you whether you're moving or standing still. Physics works the same in all inertial reference frames. The second postulate was the one that detonated 2 centuries of certainty. Einstein stated that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. Not approximately the same, exactly the same. Always. Every observer, moving or stationary, fast or slow, measures light at exactly 300,000 kilometers per second. This sounds harmless until you trace what it actually requires. Imagine you're standing on the ground and I shine a flashlight past you. You measure the light moving at 300,000 kilometers per second. Now imagine you're flying past me in a spacecraft at half the speed of light, 150,000 kilometers per second, and I shine the same flashlight in the same direction. In Newton's universe, you should measure the light passing you at only 150,000 kilometers per second. Your speed subtracted from the light's speed gives the relative speed. That is simple arithmetic. The same math that works perfectly for baseballs and bicycles and trains. But Einstein said no. You still measure the light at 300,000 kilometers per second. Not 150,000. The full speed. Even though you yourself are already hurtling through space at half the speed of light in the same direction the light is traveling. Now, turn it around. You fly directly toward the flashlight beam at half the speed of light. In Newton's universe, you would measure the light approaching at 450,000 kilometers per second. The light's speed plus your speed, but Einstein said no. Still 300,000. Always 300,000. No matter how fast you move, no matter which direction, the number never changes. This seems to violate basic arithmetic. It seems flatly impossible. If you're walking at 5 kilometers per hour along the aisle of a train, moving at 100 kilometers per hour, a person on the ground sees you moving at 105 kilometers per hour. The speeds add. That is how the world works. We have verified it with every moving object humans have ever measured. How can it possibly be that light does not follow this rule? Here is Einstein's answer, and it is the single most important insight in the history of modern physics. If the speed of light truly is the same for all observers, and experiment after experiment confirms that it is, then something else must give. Speed is distance divided by time. If you and I are moving relative to each other, and we both measure the same beam of light at the same speed, then we must disagree about the distance the light travelled, or about the time the journey took, or both. And that is precisely what happens. Two observers moving relative to each other do not measure the same distances. They do not measure the same time intervals. They do not agree on whether two events happened at the same moment or at different moments. These disagreements are not errors. They are not illusions. They are not problems with their clocks or their rulers. Space and time themselves are genuinely, physically, measurably different for observers in different states of motion. The distances are different, the durations are different, and they must be different because that is the only way for both observers to measure the same speed of light. Newton's absolute space is gone. Newton's absolute time is gone. The fixed stage has been pulled out from under the universe. The universal clock has been smashed. And what remains standing amid the wreckage is a single, experimentally unbreakable constant. The speed of light. 300,000 kilometers per second for everyone, everywhere, always. And it is the stubbornness of that constant, its absolute refusal to change for anyone under any circumstances, that forces space and time to become flexible, relative, and tangled up with each other in ways no one before 1905 had imagined. What Einstein had uncovered was not just a correction to Newton, it was a doorway. And on the other side of that doorway lay a reality where space and time are not two separate things that happen to coexist in the same universe. They are two aspects of a single entity. They trade against each other. They flex in concert. You cannot touch one without disturbing the other. Every time you move through space, you pay for that motion in time. And every measurement ever performed at high speeds has confirmed this. The clocks aboard aircraft have shown it. Subatomic particles raining through Earth's atmosphere have shown it. The satellites guiding your car through traffic show it every single second of every single day. And all of it, every demonstration, every experiment, every confirmation, traces back to one stubborn, unbreakable fact that shattered 2 centuries of certainty. Light travels at the same speed for everyone, always, no matter what. So what does it actually mean in physical terms for space and time to flex? What happens to reality once you accept that the speed of light is truly constant for everyone, regardless of their motion? The consequences are specific, measurable, and deeply strange. They have been confirmed by experiment beyond any reasonable doubt, and they all flow from one source, the stubbornness of light. The most direct consequence is this: moving clocks run slow. Not broken clocks, not poorly calibrated clocks. Perfectly functioning, exquisitely precise clocks that are doing exactly what they were built to do. If a clock is moving relative to you, it ticks more slowly than your own clock. Time itself passes more slowly for that moving clock. This is not a metaphor. It is not a trick of perception or a measurement error. It is a physical fact about the rate at which time unfolds, and it is a mathematically unavoidable consequence of the speed of light being the same for every observer. Here is why. Imagine the simplest possible clock. Take 2 mirrors, one positioned above the other, and bounce a single pulse of light between them. Every time the light pulse hits the bottom mirror, that counts as one tick. This clock is nothing but light traveling a known distance at a known speed. It is the purest timekeeping device imaginable, because its ticks are defined entirely by the speed of light and the distance between the mirrors. There are no gears to jam, no springs to weaken, no batteries to drain. It is just light bouncing between two mirrors, measuring time with absolute precision. Now set this light clock on a table next to you. You are both stationary. The light bounces straight up to the top mirror and straight back down to the bottom mirror. Up, down, tick, tick, tick. The path the light travels each tick is simply twice the distance between the mirrors. Straight up, straight down. Clean and simple. Your clock keeps perfect, steady time. Now put an identical light clock on a train moving past you at tremendous speed. From the perspective of a passenger riding on that train, the light inside their clock is still bouncing straight up and straight down, exactly as it does in your stationary clock. The passenger sees nothing unusual. Their clock ticks at the normal rate. Their time flows normally. Everything aboard the train proceeds as expected. But from your perspective, standing on the ground watching the train streak past, something profoundly different is happening. The train is moving forward. So by the time the light pulse travels upward from the bottom mirror to the top mirror has moved forward with the train. The light cannot travel straight up, because the mirror it is heading toward is no longer directly above where the light started. Instead, the light travels along a diagonal path, angled forward, reaching the top mirror at its new position farther down the track. When the light bounces back down, the bottom mirror has also moved forward. So the return path is also diagonal, up and forward, then down and forward. 2 diagonal legs instead of 2 straight vertical legs. This is where simple geometry takes hold. A diagonal path is always longer than a straight vertical path. If the vertical distance between the mirrors is the same in both clocks, and it is because the mirrors are identical, then the diagonal path the light must travel in the moving clock is genuinely measurably longer than the straight path in the stationary clock. You can calculate exactly how much longer using the Pythagorean theorem, the same mathematics you learned in school for finding the longest side of a right triangle. The faster the train moves, the more the light path tilts forward, and the longer the diagonal becomes. And here is where the constancy of the speed of light detonates the old picture of reality. That light inside the moving clock is not traveling faster to compensate for the longer path. It cannot travel faster. It is light. It moves at 300,000 kilometers per second. Always. For everyone. No exceptions. The speed of light is not adjustable. It does not care that the geometry has changed. It does not speed up because the path is longer. It moves at exactly the same speed it always moves. The light is covering a longer path at exactly the same speed. That means each tick takes longer to complete. The moving clock ticks more slowly than your stationary clock. Not because anything is wrong with it, not because the mirrors are misaligned or the light pulse has degraded, but because the geometry of the light path, combined with the absolute refusal of light to change its speed, forces each tick to consume more time from your perspective. Time itself passes more slowly for the moving clock. This is time dilation. And this is not a peculiarity of light clocks. Every clock, every process, every physical phenomenon runs slower when moving relative to you. Mechanical clocks, digital watches, atomic clocks, biological clocks, all of them slow down by exactly the same factor. This must be true, because if it were not, you could use the disagreement between different types of clocks to determine some absolute standard of rest, some reference frame that is truly stationary. But the first postulate of relativity says no such thing exists. All inertial reference frames are equally valid. The laws of physics are identical in all of them, so all clocks must slow down together, identically by the same factor. Time itself is what slows down, not any particular mechanism for measuring it. Heartbeats slow, chemical reactions slow, the decay of radioactive atoms slows, aging slows. Everything that unfolds in time proceeds more slowly for a moving observer, as seen by a stationary one. And here's the part that twists your intuition into a knot. From the perspective of the passenger on the train, it is your clock that is moving. They are the stationary one. You are the one rushing past them. And from their equally valid perspective, your clock is the one ticking slowly. This is not a contradiction. It is a direct consequence of the fact that there is no absolute rest. No observer is more correct than any other. Each observer genuinely, physically correctly measures the other's clock running slow. Both are right. Both measurements are real. The second consequence follows just as inevitably. Moving objects shrink along their direction of motion. This is called length contraction. If a spaceship flies past you at high speed, you would measure it to be physically shorter along its direction of travel than the astronauts inside would measure it to be. Not because any force has crushed it or compressed it, not because your measuring instruments are flawed, but because the geometry of space itself, as measured from your reference frame, genuinely differs from the geometry measured by the astronauts. The ship is shorter in your reference frame. The distance between its nose and its tail is less than what the astronauts measure when they walk from one end to the other. And from the astronaut's perspective, looking back at you and your ruler is you and your measuring equipment that are contracted. Both observers are correct. Length, like time, is relative. It depends on your state of motion. The third consequence is perhaps the strangest of all. Simultaneity itself is relative. Two events that happen at the same time according to one observer may happen at genuinely different times, according to another observer in motion relative to the first. Imagine two lightning bolts strike a train track simultaneously, one hitting the front of a moving train and one hitting the rear, as measured by a person standing on the platform watching the train pass. A passenger seated in the exact middle of that train is moving toward the point where the front strike occurred, and away from the point where the rear strike occurred. Light from the front strike reaches the passenger first, because the passenger is moving toward it. Light from the rear strike reaches the passenger later, because the passenger is moving away from it. And since the speed of light is identical in both directions, the only consistent conclusion is that the front strike genuinely happened first in the passenger's reference frame. Not appeared to happen first. Actually happened first. Two events. Same moment for one observer, different moments for another. Neither observer is mistaken. There is no absolute fact about whether the events were simultaneous. Simultaneity depends on how you are moving. Time is not a universal sequence of moments that the entire cosmos agrees on. It is local. It is personal. It is relative. All three of these effects, time dilation, length contraction, and the relativity of simultaneity, are consequences of exactly one thing: the speed of light being the same for all observers. That single fact forces space and time to flex, stretch, compress, and trade against each other in whatever way is necessary to preserve light's constant speed. The speed of light is the fixed point of the universe. Everything else adjusts around it. Now here is the insight that ties everything together and makes the title of this story land as measured fact rather than philosophical slogan. There is a way to understand all of these effects as one elegant trade. And it goes like this. Right now, as you sit listening to this, you are moving. You might feel completely stationary, but you are moving through time. Every second, you travel 1 second into the future. That is motion. It is not motion through space, but it is motion through the fabric of reality. You are gliding forward through time at a steady rate, and that glide is as real as any movement through space. In fact, everything in the universe moves through the combined fabric of space-time at exactly the same total speed. That speed is the speed of light. Always, without exception. You, a distant star, a rock on the moon, a grain of sand, a photon crossing a galaxy, all of it moves through space-time at 300,000 kilometers per second. This sounds impossible. You are clearly not moving through space at the speed of light. You are sitting still. And that is exactly the point. You are not moving through space at the speed of light. You are moving through time at the speed of light. All of your motion through space-time is aimed in the time direction. Think of it as a budget. A fixed budget that can never be increased or decreased. Your total speed through space-time is always exactly the speed of light. You can allocate that budget between two directions, space and time, in any proportion you like. But the total is locked. It never changes. Imagine you were driving north across a flat plain at 100 kilometers per hour. All of your speed is directed northward. Now you turn the wheel slightly and start angling northeast. Your total speed is still 100 kilometers per hour, but now some of that speed is directed eastward. The more you turn east, the less of your speed is directed north. If you turn due east, all of your speed is eastward, and your northward progress drops to 0. Your total speed never changed. Only the direction did. And what you gained in one direction, you lost in the other. This is exactly how motion through space-time works. When you are sitting still in space, your entire space-time speed budget is directed through time. You move through time at the maximum possible rate. Your clocks tick as fast as they can. Your aging proceeds at full speed. The moment you begin moving through space, some of your fixed budget gets redirected from the time direction to the space direction. Your motion through time slows down. Your clocks tick a fraction more slowly. Time passes slightly less quickly for you. The faster you move through space, the more of your budget is diverted from time, and the slower time passes. At everyday speeds, this reallocation is fantastically small. Walking at 5 kilometers per hour, the fraction of your space-time budget directed into space is so microscopically tiny that the reduction in your motion through time is unmeasurable by any instrument you could carry. At jet aircraft speeds, a few hundred kilometers per hour, the slowdown amounts to a few billionths of a second over an entire flight. Real, but barely detectable even with atomic clocks. But increase your speed, and the trade becomes impossible to ignore. At 10% of the speed of light, roughly 30,000 kilometers per second, your clocks run about 0.5% slow. At 90%, time passes for you at less than half the rate it passes for someone at rest. At 99.9%, time nearly stops. Almost your entire space-time budget has been redirected into spatial motion, leaving almost nothing for the time direction. And at exactly the speed of light, the trade is complete. A photon allocates its entire space-time budget to motion through space. Nothing remains for motion through time. For a photon, time does not pass at all. A photon emitted by a star a million light-years away and absorbed by your eye after crossing that vast distance experiences zero elapsed time during its journey. From the photon's perspective, emission and absorption are the same event. It aged 0 seconds during a trip that you measure as lasting a million years. All of its motion was through space, none was through time. This is the trade. This is what it physically means for space and time to be the same thing. They are not identical. Space is not time, and time is not space. But they are two inseparable components of a single quantity, total motion through space-time, and that total is always fixed at the speed of light. Motion through space is purchased by surrendering motion through time. Speed up in space and your clock slows down. Come to rest in space and your clock runs at maximum speed. Every effect of special relativity, time dilation, length contraction, the relativity of simultaneity, is this single trade expressing itself in a different form. One mechanism, one constant, one fabric, and none of this is theory waiting for verification. This trade has been directly measured with atomic clocks on commercial aircraft. In 1971, physicist Joseph Haffel and astronomer Richard Keating carried out one of the most elegant physics experiments of the 20th century. They loaded 4 cesium beam atomic clocks into carrying cases and flew them around the world on regular commercial airline flights. First eastward, then westward. Identical reference clocks remained on the ground at the United States Naval Observatory in Washington, keeping time in the laboratory while their twins circled the planet at 30,000 feet. The logic was straightforward. Eastward flying clocks were adding the airplane's speed to Earth's own rotational speed, so they moved faster relative to the non-rotating center of the planet than the ground clocks did. Westward flying clocks were partially opposing Earth's rotation, so they moved more slowly relative to the center. Different speeds through space mean different portions of the space-time budget allocated to spatial motion, which means different rates of passage through time. Einstein's equations made specific predictions for how much time difference should appear, accounting for both the velocity of the aircraft and the altitude at which they flew. Altitude matters too. Through a gravitational mechanism we will reach shortly. The predictions were precise, measured in nanoseconds, billionths of a second. When the flying clocks returned and were compared to the ground clocks, the results matched. The eastward flying clocks had lost about 59 nanoseconds relative to the ground clocks. The westward flying clocks had gained about 273 nanoseconds. The numbers agreed with Einstein's predictions within the uncertainty of the measurements. Billionths of a second, recorded and verified across multiple flights. These were not exotic laboratory instruments isolated in a pristine physics facility. These were atomic clocks sitting in purchased passenger seats on Pan American and Trans World Airlines flights, surrounded by ordinary travelers who had no idea they were participating in one of the most important experiments of the century. The universe does not require a dramatic setting. The same physics that would govern a spacecraft at half the speed of light governs a jetliner cruising at 900 kilometers per hour. The effect is smaller, enormously smaller, but it is the same mechanism. And by 1971, cesium clocks were precise enough to catch it in the act. But nature had already been performing a far more dramatic version of this experiment, continuously, for as long as cosmic rays have been striking Earth's atmosphere. The demonstration involves particles called muons. Roughly 15 kilometers above your head right now, high-energy protons from deep space are slamming into nitrogen and oxygen molecules in the upper atmosphere. These collisions produce cascading showers of secondary particles, among them muons. A muon is an unstable particle, a heavier cousin of the electron. It decays with a precisely measured half-life of about 2.2 microseconds. That means, if you start with a large collection of muons at rest, half of them will have decayed after roughly 2.2 millionths of a second. 2.2 microseconds is extraordinarily brief. Even traveling at 99.8% of the speed of light, which is approximately how fast these atmospheric muons move, a simple calculation says a muon should travel only about 660 meters before half the original population decays. From 15 kilometers altitude to sea level, the muons would need to survive for roughly 50 microseconds. Over 20 half-lives. After 20 half-lives, the surviving fraction of any particle population is vanishingly small. Essentially none of them should reach the ground, but enormous numbers of muons reach the ground. Detectors at sea level register them constantly. This is not a subtle discrepancy. The number of muons arriving at the surface is vastly, dramatically larger than what a non-relativistic calculation allows. Something is stretching their lives. That something is the trade. These muons are blazing through space at 99.8% of the speed of light. Nearly their entire space-time budget is allocated to spatial motion. Almost nothing remains for motion through time. From our perspective on the ground, the muons' internal clocks run roughly 15 to 20 times slower than they would at rest. Their 2.2 microsecond half-life stretches to 40 or 50 microseconds in our reference frame. That is more than enough time for them to cross the full 15 kilometers of atmosphere and reach our detectors. And here is where the unity of this physics becomes beautiful. From the muon's own perspective, the explanation is completely different in detail, but identical in substance. From the muon's frame, its own clock runs at the normal rate. It still has only about 2.2 microseconds to live. But from its perspective, the atmosphere is length contracted. The 15 kilometers between the top of the atmosphere and the ground is not 15 kilometers in the muon's reference frame. That distance is compressed along the direction of motion, squashed down to only about 900 meters or less. The muon easily crosses this contracted distance within its short lifetime. Two perspectives, two different descriptions, one invoking time dilation, the other invoking length contraction, both producing exactly the same observable result. The muons reach the ground. Both descriptions are correct. Both are the same trade, the same mechanism, the same constant speed of light, forcing space and time to flex, seen from two different vantage points. This is not a thought experiment. This is happening above your head at this moment. Moons are raining down through the atmosphere right now, surviving a journey they have no classical business surviving because time and space are trading against each other exactly as Einstein said they must. Particle accelerators offer even more controlled and precise confirmation. At facilities like CERN, protons are accelerated around underground rings kilometers in circumference, reaching speeds of 99.9999% of the speed of light. At those speeds, virtually the entire space-time budget is consumed by spatial motion. Almost nothing remains for time. Unstable particles that should decay in millionths of a second at rest survive long enough to circle the ring thousands of times, covering distances of many kilometers, because time is barely passing for them. Their measured lifetimes in the laboratory frames stretch by factors of thousands, sometimes tens of thousands, compared to their lifetimes at rest, and the extension matches Einstein's equations exactly, not approximately, not within a rough margin, exactly, to the limits of measurement precision. These experiments have been repeated thousands of times at accelerator facilities across the world over many decades. The agreement between prediction and observation is extraordinary. One experiment stands out for its precision. At CERN in 1977, physicists injected muons into a storage ring, a circular tunnel designed to keep the particles circling at a precisely controlled speed. The muons traveled at 99.94% of the speed of light. At that speed, Einstein's equations predict their lifetime should be stretched by a factor of about 29.3 compared to muons at rest. The experimenters measured the decay rate of these circling muons with painstaking accuracy, counting how many survived after each lap, tracking the exponential decline of the population over thousands of orbits. The result agreed with Einstein's time dilation formula to better than 2 parts in 1,000. Not 2%, 2 parts in 1,000. That is a match between theory and measurement so tight that it leaves essentially no room for an alternative explanation. The muons lived longer by exactly the factor the space-time trade demands at that speed. Their internal clocks ran slow by exactly the amount the equations require. This single experiment, performed with particles circling a ring in a laboratory, confirmed the same physics that Haffel and Keating measured aboard commercial aircraft, but with a precision roughly 1,000 times greater. Every one of these measurements, the atomic clocks on aircraft, the muons raining through the atmosphere, the particles circling accelerator rings, is the same physics, the same trade, the same mechanism. The speed of light locks your total motion through space-time to a fixed value. Redirect more of that motion into space, and less remains for time. An aircraft moves so slowly compared to light that the effect amounts to billionths of a second. A muon moves so fast that its life stretches by a factor of 20. A particle at CERN moves so close to light speed that its lifetime extends by thousands. Different volumes, same mechanism, same equation, same constant anchoring everything. Newton's universe cannot produce any of these results. In Newton's universe, clocks always agree regardless of their motion. Moons always decay at the same rate whether they are sitting still or hurtling at nearly the speed of light. Atomic clocks on aircraft read the same as clocks on the ground. None of that is what we observe. Every measurement contradicts the old picture. Every measurement confirms the new one. Space and time are not two separate things that merely coexist in the same universe. They are two faces of a single fabric, and your motion through that fabric is always at the speed of light. Where you aim that motion, how much goes to space and how much goes to time, determines how fast your clocks tick, how long your rulers measure, and whether two distant events are simultaneous or separated. All of it traces back to one unbreakable constant and one inescapable trade. And the evidence for that trade is not hidden in some inaccessible corner of theoretical physics. It is falling from the sky above you right now. It is orbiting Earth in satellites. And it was once riding in a purchased seat on a Pan-American flight, ticking quietly in a carrying case while the universe proved Einstein right. By 1908, just 3 years after Einstein published his theory of special relativity, a mathematician named Hermann Minkowski saw something in the equations that Einstein himself had not fully appreciated. Minkowski had actually been one of Einstein's former professors, and he was struck by the mathematical structure hiding beneath the physics. He stood before an audience of scientists and made a declaration that sounded more like poetry than mathematics. He told them that from this point forward, space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. What Minkowski had recognized was that Einstein's equations were not just saying that space and time affect each other. They were saying that space and time are components of a single, four-dimensional object, not 3 dimensions of space alongside a separate flow of time. 4 dimensions woven together into one fabric, spacetime, a single entity that contains both spatial distances and temporal durations as inseparable parts of its structure. This was not a philosophical suggestion or a convenient way of organizing the math. It was a physical claim with measurable consequences. And the key to understanding it, the concept that makes the entire unification land as fact rather than metaphor, is something called the space-time interval. To understand the interval, start with something familiar. At ordinary distance, if you have 2 points on a flat surface, you can calculate the straight line distance between them using the Pythagorean theorem. Take the difference in their horizontal positions, square it. Take the difference in their vertical positions, square it. Add the 2 squared differences together. Take the square root. That gives you the distance. This works regardless of how you orient your coordinate system. You can tilt your grid, rotate it, slide it sideways, and the distance between the 2 points never changes. The individual coordinates change. The horizontal and vertical differences shift around as you rotate your grid. But the combined distance remains the same. It is an invariant, a quantity that all observers agree on no matter how they set up their measurement system. This is so natural that you probably never think about it. If someone tells you 2 cities are 100 kilometers apart, you do not ask which direction they measured from. The distance is the distance. It does not depend on whether you orient your map north-south or tilt it at some angle. The individual coordinates of each city depend on your map orientation, but the distance between them does not. Now, in Einstein's relativity, something deeply analogous happens, but with a crucial twist. When 2 events occur in space-time, 2 firecrackers going off, 2 lightning bolts striking, 2 atoms emitting photons, anything at all, different observers moving at different speeds will disagree about where those events happened in space and when they happened in time. One observer says the events were separated by a certain spatial distance and a certain time interval. Another observer, moving relative to the first, measures different spatial separation and different time separation. This is the relativity of space and time. Distances change, durations change, even the order of events can change if the events are far enough apart. But there is one quantity that does not change. One number that every observer in the universe, regardless of their motion, will calculate and agree on. This is the space-time interval. The interval combines the spatial separation and the temporal separation of two events into a single number, and that number is the same for everyone. It is the true distance between events in four-dimensional space-time, just as ordinary distance is the true distance between points on a two-dimensional map. The individual components change depending on your perspective. The spatial part shifts. The temporal part shifts. But the combined interval is invariant. Here is where the crucial twist enters. In ordinary geometry, when you calculate distance, you add the squared components. Horizontal squared plus vertical squared. But in space-time geometry, you do not add, you subtract. The interval is calculated by taking the time separation squared and subtracting the space separation squared. Or equivalently, taking the space separation squared and subtracting the time separation squared, depending on which convention you prefer. The sign differs between conventions, but the subtraction is what matters. This minus sign is not an arbitrary mathematical choice. It is the fingerprint of how space and time differ from each other within their shared fabric. Space and time are part of the same structure, but they contribute to that structure with opposite signs. They push against each other. They trade. This is the mathematics behind the speed budget we explored earlier. When you increase your spatial separation between two events, the time component must adjust in the opposite direction to keep the interval unchanged. More space, less time, less space, more time. The interval sits there, unchanged, while space and time seesaw around it. Let me make this concrete. Imagine two events. A firecracker explodes at a certain location and a certain moment, and then a second firecracker explodes somewhere else at a later moment. You, standing still, measure the spatial distance between the two explosions and the time between them. You calculate the interval. Now a friend flies past in a spacecraft at enormous speed. From her perspective, the spatial distance between the two explosions is different, the time between them is different, the two events might even have a different temporal order depending on the specifics. But when she calculates the interval using her measurements, plugging her different space numbers and her different time numbers into the same formula, she gets exactly the same answer you did. This is the same kind of invariance as ordinary distance on a map, extended into 4 dimensions and given that crucial minus sign. Rotate your coordinate axes on a flat map, and the individual coordinates of a point change, but the distance stays fixed. Boost your velocity in space-time, and the individual space and time coordinates of an event change, but the interval stays fixed. The interval is the true, observer-independent reality. Space alone is not invariant. Time alone is not invariant. Only the combination, the interval, the 4-dimensional space-time structure is real in the deepest sense. This is what it physically means for space and time to be the same thing. Not that a meter equals a second. Not that you can swap one for the other casually. But that neither one alone is the full story. Neither one alone is invariant. Neither one alone is something all observers agree on. Only together, combined into the interval with that critical minus sign, do they form a quantity that is absolute, universal, and observer-independent. Minkowski's insight was that this interval, this 4-dimensional structure, is the actual geometry of reality. What Newton called absolute space and absolute time were just projections, shadows, partial views of the true 4-dimensional fabric. Different observers slice space-time differently, like cutting a loaf of bread at different angles. Each cut gives a different cross-section, a different view of what counts as space and what counts as time. But the loaf itself, the full 4-dimensional block, is the same for everyone. This might sound abstract. It might sound like mathematics that only matters inside a university lecture hall. But there is a piece of technology in your pocket right now, or on the dashboard of your car, or embedded in the phone you carry everywhere, that would fail catastrophically within hours if this 4-dimensional structure were not real. That technology is the Global Positioning System, GPS. The GPS system consists of a constellation of roughly 31 satellites orbiting Earth at an altitude of about 20,200 kilometers. Each satellite carries multiple atomic clocks, extraordinarily precise timekeeping devices accurate to within a few billionths of a second per day. Your GPS receiver, the chip inside your phone or car navigation unit, determines your position by receiving timing signals from at least 4 of these satellites simultaneously. Each signal tells the receiver what time the satellite sent it and where the satellite was at that moment. By comparing the arrival times of signals from multiple satellites, and knowing that the signals travel at the speed of light, the receiver calculates how far it is from each satellite. With 4 or more distance measurements, it pinpoints your position on the surface of Earth to within a few meters. The entire system depends on extraordinarily precise timekeeping. A timing error of just 1 microsecond, 1/1,000,000th of a second, translates to a position error of about 300 meters, because that is how far light travels in a microsecond. For GPS to give you accuracy of a few meters, the timing must be accurate to roughly 10 billionths of a second, 10 nanoseconds. That is the margin. There is no room for unaccounted physics. And here is where space-time stops being abstract and becomes a daily engineering requirement. The GPS satellites are moving. They orbit Earth at about 14,000 kilometers per hour. That is fast by everyday standards, but still a small fraction of the speed of light. The velocity-based time dilation from special relativity, the trade between motion through space and motion through time, causes the satellite clocks to tick slightly slower than identical clocks on the ground. The effect is about 7 microseconds per day, 7 millionths of a second. That sounds tiny, but remember, 1 microsecond equals 300 meters of position error. 7 microseconds of uncorrected time dilation would introduce about 2 kilometers of position error per day. Your GPS would be off by kilometers, and the error would grow larger every single day. But that is only half the story. The satellites are also higher up, farther from Earth's center, sitting in a weaker gravitational field than clocks on the ground. And gravity, as we are about to discover, also affects the passage of time. Clocks in weaker gravity tick faster. This gravitational effect is larger than the velocity effect, and runs in the opposite direction. Clocks on the GPS satellites tick faster than ground clocks by about 45 microseconds per day because of their altitude. The net effect, combining the velocity slowdown and the gravitational speedup, is that GPS satellite clocks run faster than ground clocks by about 38 microseconds per day. 38 microseconds. That is roughly 11 kilometers of position error per day if left uncorrected. Your GPS navigation would drift off course by 11 kilometers every single day. Within a week, it would be useless. Within a month, it would be placing you in a different city. GPS works because the system's engineers account for both of these relativistic effects. Every GPS satellite carries clocks whose tick rate has been deliberately adjusted before launch to compensate for the predicted combination of velocity-based and gravity-based time dilation, and the receivers apply additional corrections in real time as they process signals. The corrections are not optional extras bolted onto an otherwise functional system. Without them, the system does not function. GPS is a machine that runs on the geometry of four-dimensional space-time. It works because space and time are one fabric, because motion through that fabric follows the rules Einstein and Minkowski described, and because the engineers who designed it took those rules seriously. Every time you use GPS to find a restaurant, navigate a highway, or track a delivery, you are relying on the physical reality of space-time. The fact that GPS gives you accurate directions is direct, daily, continuously verified proof that space and time are not separate, that moving clocks run slow, and that gravity affects the passage of time. You carry the evidence in your pocket. Now we come to the bridge. Everything we have discussed so far, time dilation, length contraction, the space-time interval, the GPS corrections for velocity, belongs to the domain Einstein described in 1905. Special relativity. It handles motion at constant velocity through flat space-time. Space-time without gravity. But we live in a universe where gravity is everywhere. Every planet, every star, every moon pulls on the fabric of the cosmos. And in 1915, Einstein extended his theory to include gravity, producing general relativity. And what he found was extraordinary. The key insight arrived through what Einstein later called the happiest thought of his life. He imagined a person falling freely, stepping off the roof of a building. During the fall, before hitting the ground, the person would feel weightless. A ball released from the falling person's hand would not drift away or fall toward the ground faster. It would float alongside them, motionless relative to them, exactly as objects float inside the International Space Station. In that brief, terrifying moment of free fall, gravity has vanished. Not really, of course. Gravity is still pulling the person toward the ground. But locally, inside the falling person's small region of space, there is no experiment that can distinguish free fall in a gravitational field from floating in empty space, far from any massive object. Gravity and acceleration are locally indistinguishable. This is the equivalence principle, and Einstein saw that it cut both ways. If free fall erases the effects of gravity, then acceleration creates the effects of gravity. Stand inside a closed elevator in deep space, far from any star or planet, and have someone pull the elevator upward with a constant acceleration. You would feel your feet pressed to the floor. A ball released from your hand would appear to fall to the floor. A beam of light crossing the elevator would curve slightly downward, bending toward the floor, because the elevator is accelerating upward while the light crosses it. Everything inside that accelerating elevator mimics what happens in a gravitational field. You cannot tell the difference. No experiment you perform inside the elevator can determine whether you are in an accelerating elevator in empty space or standing still on the surface of a planet. But Einstein pushed the thought further, and this is where the equivalence principle stops being a curiosity and becomes the key that unlocks gravity itself. If acceleration and gravity are truly indistinguishable, then anything that happens in an accelerating elevator must also happen in a gravitational field. This is not optional. If there were any difference, any experiment that could tell the two apart, the equivalence principle would be violated. So whatever acceleration does to physics, gravity must do as well. Consider what acceleration does to light. You are standing inside that closed elevator in deep space, being pulled upward with constant acceleration. Someone outside shines a beam of light horizontally through a small window on one side of the elevator. The light enters at a certain height above the floor, but the elevator is accelerating upward while the light crosses the cabin. By the time the light reaches the far wall, the elevator has moved upward slightly. From your perspective inside, the light did not travel in a straight horizontal line. It followed a curved path, bending downward toward the floor. The light entered at one height and struck the opposite wall at a slightly lower height. Light curved in the accelerating elevator. Now apply the equivalence principle. If there is no experiment that can distinguish acceleration from gravity, and light curves in an accelerating elevator, then light must also curve in a gravitational field. A beam of light passing near a massive object should bend toward that object. Not because light has mass in the Newtonian sense, not because some force is pulling on photons, but because the space-time through which the light travels is itself curved by the massive object, and the light is following the straightest available path through that curved geometry. The path looks curved to us because we are thinking in three-dimensional space. In four-dimensional space-time, the light is following a geodesic, the closest thing to a straight line that curved geometry allows. This prediction was tested directly in 1919 during a total solar eclipse. The British astronomer Arthur Eddington led 2 expeditions, one to the island of Príncipe off the west coast of Africa, and one to Sobral in Brazil, to photograph stars near the edge of the eclipsed sun. During a total eclipse, the sky darkens enough to see stars that appear close to the sun's position in the sky. If Einstein was right, the sun's mass should curve the space-time around it, bend in the light from those stars as it passes near the sun on its way to Earth. The stars should appear to be in slightly different positions than where they actually are, shifted outward from the sun because their light was bent inward as it passed through the curved space-time near the solar surface. Eddington's measurements confirmed the prediction. The stars near the sun's edge were displaced by approximately the amount general relativity demanded. The result was not perfectly precise by modern standards, and there was considerable uncertainty in the measurements. But the deflection was clearly present and clearly matched Einstein's prediction rather than Newton's, which predicted only half as much bending. The announcement made Einstein an international celebrity overnight. But more importantly, it confirmed that gravity bends light, that space-time itself is curved by mass, and that the equivalence principle was not just an abstract thought experiment, but a physical reality with observable consequences. Since then, gravitational light bending has been confirmed with extraordinary precision. Quasars, intensely bright objects billions of light years away, sometimes appear as multiple images in the sky because a massive galaxy sitting between the quasar and Earth bends the quasar's light around it like a lens. This is called gravitational lensing, and it produces arcs, rings, and multiple copies of the same distant object, all created by the curvature of space-time around the intervening mass. These are not theoretical predictions, they are photographs. We have images of Einstein rings, near-perfect circles of light produced when a distant source, a lensing mass, and the observer are almost perfectly aligned. The light from the distant source is bent equally in all directions around the lensing mass, producing a ring of light that could not exist if space-time were flat. Gravitational lensing is now used as a routine tool in astronomy. Researchers use the bending of light to weigh galaxy clusters, to detect dark matter that emits no light of its own, and to magnify extremely distant galaxies that would otherwise be too faint to observe. The curvature of space-time predicted by Einstein is not a subtle, theoretical nicety. It is a working instrument, a cosmic magnifying glass used every day in observational astronomy. All of this flows from the equivalence principle and one simple chain of logic. If acceleration and gravity are indistinguishable, and acceleration curves the path of light, then gravity must curve the path of light. And if gravity curves the path of light, then gravity is not a force pulling on objects through flat space. Gravity is the curvature of space-time itself, and light, matter, and everything else simply follows the geometry. This was Newton's picture finally overthrown. Newton had described gravity as a force pulling objects toward each other across empty space, an invisible hand reaching across the void to tug on distant masses. Einstein saw something entirely different. There is no hand. There is no force reaching through the void. There is only the shape of the fabric, and everything in the universe follows that shape. Here is the idea. Massive objects, stars, planets, anything with mass or energy, curve the space-time fabric around them. They do not reach out and pull on distant objects with invisible forces. They warp the geometry of the region they occupy, and objects moving through that warped geometry follow the straightest possible paths available to them. In flat space-time, the straightest path between 2 points is a straight line, but in curved space-time, the straightest possible path can be a curve. The moon does not orbit Earth because an invisible rope of gravitational force is pulling it into a circle. The moon orbits Earth because Earth's mass has curved the space-time around it, and the moon is following the straightest available path through that curved geometry. It is moving in a straight line through curved four-dimensional space-time. And that straight line, projected into our three-dimensional view of space, looks like an orbit. This is a stunning reimagining of one of the most familiar phenomena in the universe. Gravity is not a force acting within space-time. Gravity is a property of space-time itself. It is the shape of the fabric. Where the fabric is flat, objects move in straight lines. Where the fabric is curved, objects follow curved paths. The curvature tells matter how to move. Matter tells the fabric how to curve. And because this is space-time that curves, not just space, gravity affects time as well as trajectories. This is gravitational time dilation. Clocks closer to a massive object, deeper in the gravitational well where space-time is more severely curved, tick more slowly than clocks farther away. Time passes at different rates at different heights in a gravitational field. This is not a small, exotic effect visible only at the extremes of astrophysics. It is happening to you right now. Your feet, being slightly closer to Earth's center than your head, exist in slightly more curved space-time. Time passes for your feet at a marginally slower rate than it passes for your head. The difference is absurdly small for a human body, roughly a nanosecond or so per year between head and feet. But it is real, and modern atomic clocks are precise enough to measure it over height differences as small as a single step on a staircase. This gravitational time dilation is the second component of the GPS correction we discussed. The satellites orbit at 20,200 kilometers above the surface, far from Earth's center, where space-time is less curved than at sea level. Their clocks tick faster than ground clocks by about 45 microseconds per day, because they sit in weaker gravity, in less curved space-time, where time flows more freely. This gravitational speedup is larger than the velocity-based slowdown and runs in the opposite direction. Both effects are real, both have been measured independently, and both must be accounted for simultaneously, because both emerge from the same four-dimensional fabric. The velocity correction comes from special relativity, the geometry of motion through flat spacetime. The gravitational correction comes from general relativity, the geometry of curved spacetime itself. The GPS system needs both corrections, from both aspects of the theory, applied at the same time, every second of every day, or it fails. The system's continued accuracy is daily proof that both halves of the theory are correct. And here is the deep unity. The velocity-based time dilation and the gravitational time dilation are not two separate phenomena that happen to coexist. They are two expressions of the same underlying reality. Both arise because space-time is a single four-dimensional fabric, because the interval is invariant, and because the speed of light is the fixed constant around which everything else adjusts. When you move through space, you trade spatial motion for temporal motion, and your clock slows down. When you sit in a gravitational field, space-time is curved, and that curvature alters the passage of time directly. Both effects are geometry. Both effects are the fabric of space-time responding to physical conditions, motion in one case, mass in the other, while preserving the invariance of the interval and the constancy of light speed. Newton would have said that gravity pulls an apple toward the ground. Einstein says the apple follows the straightest path through curved space-time near Earth's surface, and that path leads toward the ground. Newton would have said that the moon is held in orbit by an invisible force reaching across empty space. Einstein says the moon follows the straightest path through the curved space-time geometry created by Earth's mass. Newton would have said that time flows at the same rate everywhere, regardless of gravity. Einstein says time flows at different rates depending on the curvature of space-time, which is determined by the distribution of mass and energy. And every test, every measurement, every experiment designed to distinguish between these two pictures has confirmed Einstein and contradicted Newton. Not because Newton was foolish. Newton was one of the greatest minds in human history. His framework is still used daily for most engineering applications, because at low speeds and weak gravitational fields, it is an extraordinarily good approximation. But it is an approximation. The deeper truth is Einstein's. Space and time are one fabric. That fabric curves in the presence of mass and energy. And the curvature of that fabric is what we experience as gravity. The sun does not reach across 93 million miles of space with an invisible hand to hold Earth in orbit. The sun curves the space-time around it. Earth moves through that curved space-time along the straightest available path. And that path happens to be an ellipse. The sun does not pull. The sun curves, and Earth follows the curve, not because a force compels it, but because there is no straighter path available through the geometry of reality. And this curvature is not a vague, abstract deformation. It has been measured with stunning directness. In 2011, the results of an experiment called Gravity Probe B were published after more than 4 decades of development. The experiment, launched into orbit around Earth in 2004, carried 4 gyroscopes made of nearly perfect quartz spheres, the most spherical objects ever manufactured by human hands. These gyroscopes were set spinning and then monitored with extraordinary precision as the satellite orbited Earth for more than a year. In flat space-time, a spinning gyroscope's axis should point in the same direction forever. But in curved space-time, the curvature itself should cause the gyroscope's axis to slowly drift, rotate by a tiny but predictable amount as the satellite follows its orbital path through curved geometry. Gravity probe B measured two separate effects. The first, called geodetic precession, is the drift caused by Earth's mass curving spacetime around it. The satellite moves through this curved geometry and the gyroscope axis gradually tilts. The second, called frame dragging, is even more exotic. Earth's rotation actually drags the spacetime fabric around with it slightly, like a spinning ball immersed in honey, pulling the honey along as it turns. This dragging effect is incredibly small, but Gravity Probe B detected it. Both measurements matched Einstein's predictions. The geodetic effect was confirmed to better than 1% accuracy. Frame dragging was confirmed to roughly 19% accuracy, limited by unexpected noise in the experiment, but still clearly present and consistent with general relativity. Earth does not simply sit in space-time. It curves space-time around it, and it drags that curved fabric along as it rotates. The geometry of space-time near Earth is not static. It is shaped by Earth's mass and twisted by Earth's spin, exactly as Einstein's equations demand. That geometry, that single four-dimensional fabric, curved by mass and energy, is what unites every experiment we have discussed. The atomic clocks on aircraft measured time dilation from velocity, the trade between spatial motion and temporal motion through flat spacetime. The GPS satellites measure time dilation from both velocity and gravity, requiring corrections from both special and general relativity simultaneously. The muons surviving their atmospheric descent demonstrate the velocity trade in dramatic fashion. And as we will see, clocks at different altitudes on Earth, and even the extreme environments near neutron stars, demonstrate the gravitational curvature of the same fabric, the same mechanism operating at higher and higher volumes. All of it traces back to one origin. Because every observer measures light at the same speed, space and time cannot be separately absolute. They must flex. They must trade. They must form a single fabric whose geometry, flat or curved, determines the passage of time, the measurement of distance, and the paths that objects follow through the cosmos. That fabric is space-time, and everything you have ever experienced, every heartbeat, every footstep, every sunrise, has happened within it. Right now, as you listen to this, your head is aging faster than your feet. Not by much, not by any amount you would ever notice in a human lifetime. But the difference is physically real, experimentally confirmed, and it never stops. Every second you spend standing upright, the atoms in your skull tick through time at a marginally faster rate than the atoms in your shoes. Your brain, sitting roughly 1.5 to 2 meters farther from Earth's center than the soles of your feet, exists in slightly less curved space-time. Time flows a fraction more freely up there. Your head accumulates time faster. Over the course of a 70-year life, the cumulative difference between the top of your body and the bottom amounts to roughly 90 billionths of a second, 90 nanoseconds, meaningless for daily life, unmeasurable without exquisite instrumentation, but real. This is not a thought experiment. This is not a prediction waiting for future technology to verify. Modern atomic clocks have measured this effect directly over height differences far smaller than the distance between your head and your feet. In 2010, physicists Chin-Wen Chao and colleagues at the National Institute of Standards and Technology in Boulder, Colorado, published an experiment that pushed the measurement of gravitational time dilation to an almost absurd level of precision. They used aluminum ion optical clocks, Instruments that measure time by counting the oscillations of individual aluminum atoms trapped in electromagnetic fields. These clocks are so precise that they would not gain or lose a single second in roughly 3.7 billion years, a span comparable to the age of life on Earth. Chow's team placed 2 of these clocks at different heights in their laboratory, separated by a vertical distance of just 33 centimeters. About a foot. Less than the height of a standard ruler. And they measured time passing at different rates at those 2 elevations. The higher clock ticked faster than the lower clock, by exactly the amount Einstein's general relativity predicted. 33 centimeters. 1 stair step. That is how sensitive space-time curvature is to altitude near Earth's surface. The fabric of space-time is not flat beneath your feet. It is curved, gently but measurably. And that curvature makes time pass at different rates at different heights. Not approximately. Exactly as the equations predict. The higher you go, the faster time flows. The lower you descend, the more space-time curvature compresses the passage of time. But the first direct measurement of this gravitational effect on time came decades earlier, in an experiment that is among the most elegant in all of 20th century physics. In 1959, at Harvard University, 2 physicists named Robert Pound and Glenn Repke set out to test one of the most fundamental predictions of general relativity. Einstein's theory predicted that light climbing upward through a gravitational field should lose energy, not because anything absorbs it or slows it down, but because the fabric of space-time through which the light travels is curved, and that curvature stretches the light's wavelength as it climbs. The light gets redshifted, its frequency decreases, because it is climbing out of a gravitational well. Conversely, light falling downward through a gravitational field should gain energy and blue shift. This gravitational redshift is directly linked to time dilation. If time runs slower at the bottom of a gravitational field and faster at the top, then a photon emitted at the bottom has a frequency set by the slower clock rate down there. When that photon arrives at the top, where clocks tick faster, it appears to oscillate too slowly. Its frequency is lower than expected. It is redshifted. The 2 effects, gravitational time dilation and gravitational redshift, are 2 descriptions of the same underlying physics. Measuring one confirms the other. The problem Pound and Repke faced was that the predicted effect near Earth's surface is fantastically small. Earth's gravity is relatively weak by cosmic standards. The fractional change in frequency for a photon climbing a height of roughly 22.5 meters. The height of Harvard's Jefferson Tower, where they conducted the experiment, was predicted to be about 2.5 parts in 100 trillion. That is 25 quadrillionths. A difference so tiny it seems impossible to detect. Pound and Repke's solution relied on a phenomenon discovered the previous year by the German physicist Rudolf Mersbauer. Mersbauer had found that atoms embedded in a crystal lattice could emit and absorb gamma rays with almost zero energy loss, producing spectral lines of extraordinary sharpness. This meant gamma-ray photons from iron-57 nuclei in a crystal source could be tuned to a frequency so precise that even the minuscule gravitational shift over 22.5 meters of height would push the frequency out of resonance with an identical absorber at the other end. Pound and Repke placed an iron-57 source at the top of Jefferson Tower, and an identical absorber at the bottom. They measured how the absorption changed as a function of height. Then they reversed the setup. placing the source at the bottom and the absorber at the top. By comparing the results, they isolated the gravitational effect from other potential sources of error. The result confirmed Einstein's prediction. The gravitational redshift matched the theoretical value to within 10%. 5 years later, Pound and a colleague refined the experiment and confirmed the prediction to within 1%. Light climbing out of Earth's gravity loses energy by exactly the amount that the curvature of space-time demands. Time at the bottom of the tower runs measurably slower than time at the top, over 22.5 meters. Inside a university building, gravity bends time, and Pound and Rebka caught it in the act with iron nuclei and a brick tower. Since then, gravitational time dilation has been confirmed with steadily increasing precision. Every improvement in clock technology has produced a more stringent test, and every test has confirmed the prediction. Clocks on mountaintops tick faster than clocks in valleys. Clocks on the upper floors of buildings tick faster than clocks in basements. The NIST experiment with aluminum ions at 33 centimeters showed the effect survives even when the height difference is barely larger than the length of your forearm. There is no threshold below which gravity stops affecting time. As long as there is any difference in the curvature of space-time between two locations, there is a difference in the rate at which time passes, no matter how small. And this is not a separate phenomenon from the velocity-based time dilation we measured with atomic clocks on aircraft. It is the same fabric doing the same thing for a different reason. The Haffel-Keating experiment measured both effects simultaneously. The aircraft clocks experienced velocity-based time dilation because their motion through space consumed part of their space-time speed budget. And they experienced gravitational time dilation because their altitude placed them in less curved space-time than the ground clocks. Both effects were present at the same time, operating on the same clocks, and the measured results matched the predictions that included both corrections combined. This is the deep point. There are not two different kinds of time dilation produced by two different mechanisms. There is one fabric, space-time. When that fabric is flat and you move through it, your motion through space trades against your motion through time. When that fabric is curved by mass, the curvature itself alters the rate at which time passes. Both are geometry. Both are consequences of the interval being invariant. Both trace back to the constancy of the speed of light. The aircraft clocks, the muons in the atmosphere, the satellites overhead, the aluminum ions at NIST, the gamma rays in Jefferson Tower, every single one of these experiments is measuring the same thing from a different angle. One fabric, one mechanism, different costumes. Now let us turn the volume up. Everything we have discussed so far involves weak gravity. Earth's gravitational field, by cosmic standards, is gentle. The curvature of space-time near Earth's surface is so slight that the effects on time amount to nanoseconds over years, parts per billion or less. Even at the altitude of the GPS satellites, the gravitational correction is only 45 microseconds per day. These are real and measurable, but they are whispers of the full effect. To hear the mechanism roar, you need to look at objects where gravity is not gentle. Objects where mass is packed so densely that space-time is curved severely, violently, warped so dramatically that the effects on time become impossible to overlook. A neutron star is one of the most extreme objects in the observable universe. It is what remains when a massive star, one much larger than our sun, exhausts its nuclear fuel and collapses. The outer layers of the star are blasted into space in a supernova explosion. one of the most energetic events in the cosmos. But the core does not disperse. The core collapses under its own gravity, compressed so violently that protons and electrons are crushed together to form neutrons. What remains is a sphere of matter packed to nuclear density. The numbers are staggering. A typical neutron star contains roughly 1.5 times the mass of our Sun. All of that mass, the equivalent of roughly 500,000 Earths, is compressed into a sphere roughly 20 kilometers across. 20 kilometers. About the length of a mid-sized city. You could drive across a neutron star in about 10 minutes at highway speed, assuming you could somehow survive the experience, which you emphatically could not. The density is almost beyond description. A single teaspoon of neutron star material would weigh roughly 4 billion tons on Earth's surface. 4 billion tons balance on a teaspoon. The gravitational field at the surface is roughly 200 billion times stronger than gravity on Earth. If you could stand on a neutron star, which is a purely hypothetical exercise since you would be flattened into a film of atoms thinner than a sheet of paper, you would weigh about 200 billion times more than you do right now. Neutron stars are not theoretical objects. They were predicted in the 1930s and first observed in 1967 when a graduate student named Jocelyn Bell Bernal detected a regular pulsing radio signal from a rotating neutron star, now designated PSRB 1919 plus 21. Since then, thousands of neutron stars have been catalogued. We observe them as pulsars, rapidly rotating neutron stars that sweep beams of radio waves across the sky like cosmic lighthouses. Some spin hundreds of times per second. Their existence is as well established as the existence of any other astronomical object. And on the surface of a neutron star, the curvature of spacetime is so severe that gravitational time dilation is no longer a subtle correction, measured in nanoseconds. It is enormous. A clock on the surface of a typical neutron star, one with about 1.5 solar masses, packed into a 10-kilometer radius, would tick at roughly 75 to 80% of the rate of a clock far away in flat spacetime. Time on the neutron star's surface runs about 20 to 25% slower than time in the surrounding universe, not billionths of a second per day. 20 to 25%, continuously. Every second that passes in the universe, far from the star, corresponds to only about 3/4 of a second on the star's surface. Think about what that means. If you could somehow survive on the surface of a neutron star for what felt to you like 1 year, and then return to a space station orbiting far above, you would find that roughly 15 months had passed for everyone else. You would be younger than them by several months, not because of any biological trick, because time itself passed more slowly for you. The space-time fabric where you stood was so severely curved that the rate of time was physically, measurably altered by a significant fraction. This is the aircraft clock experiment at full volume. The Haffel-Keating clocks measured a difference of nanoseconds because the aircraft flew a few kilometers above sea level at a few hundred kilometers per hour. The GPS satellites measure microseconds per day because they orbit thousands of kilometers high. The NIST clocks measured the effect over 33 centimeters in a laboratory. Each of these is the same mechanism, the curvature of space-time altering the passage of time, at progressively smaller intensities because the gravitational fields involved are progressively weaker. A neutron star takes that same mechanism and pushes it toward its limit, into a regime where the effect is no longer a rounding error, but a defining feature of the environment. 25% is not a correction. It is the physics itself, impossible to overlook, Impossible to dismiss, impossible to explain with any framework other than Einstein's curved spacetime. And even a neutron star is not the limit. The mechanism continues to intensify as gravity strengthens, push the mass into an even smaller radius, and the time dilation grows more severe. At a certain threshold, the curvature becomes so extreme that the rate of time on the surface, as measured from far away, approaches zero. A clock at that threshold would appear to stop entirely from the perspective of a distant observer. Time would seem to freeze. That threshold is the event horizon, and the object it defines is a black hole. But even without venturing to that extreme, the neutron star provides a clean, observable, measurable demonstration of gravitational time dilation operating at cosmic scale using the exact same physics that makes GPS work, and that Pound and Rebka measured inside a university tower. And this is not merely a theoretical extrapolation from Einstein's equations applied to an extreme object. We have observational evidence. We have caught gravitational time dilation in the act on neutron stars using the light they emit. When atoms on the surface of a neutron star emit light, that light has to climb out of an extraordinarily deep gravitational well to reach us. Just as Pound and Rebka measured photons losing energy as they climbed 22.5 meters inside a Harvard tower, photons climbing away from a neutron star lose a far greater fraction of their energy escaping the star's crushing gravity. The photons are gravitationally redshifted. Their wavelengths stretch, their frequencies drop. By the time the light reaches our telescopes, it carries the fingerprint of the gravitational field it escaped from. We have measured this. X-ray observatories in orbit around Earth have detected spectral lines from the surfaces of neutron stars, lines produced by iron and other elements in the neutron star's thin, searingly hot atmosphere. These spectral lines appear at lower frequencies than they should, shifted toward the red end of the spectrum by a measurable amount. The size of the redshift tells us how severely spacetime is curved at the surface, and the numbers are consistent with the predictions of general relativity for an object of that mass compressed into that radius. The same equation that describes Pound and Rebka's gamma rays losing a few 10 trillionths of their frequency over 22.5 meters also describes X-rays losing 20 to 30% of their frequency climbing away from a neutron star. Same equation, same mechanism, different volumes. Pulsars offer an even more precise testing ground, because pulsars rotate with extraordinary regularity, sweeping their radio beams across the sky with a precision that rivals atomic clocks. They can be used to test general relativity with remarkable accuracy. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, two neutron stars orbiting each other. The system, which earned them the Nobel Prize in Physics in 1993, allowed them to track the orbital dynamics with extreme precision over years and decades. The Hulse-Taylor binary system loses energy over time. The two neutron stars are spiraling closer together, their orbital period shrinking by a tiny but measurable amount each year. General relativity predicts that two massive objects orbiting each other should radiate energy in the form of gravitational waves, ripples in the space-time fabric, propagating outward at the speed of light. The energy carried away by these waves should cause the orbit to decay at a specific, calculable rate. When Hulse and Taylor compared the observed orbital decay to the prediction from general relativity, the agreement was extraordinary. matching to within a fraction of a percent over decades of observation. This was the first indirect evidence that gravitational waves exist, and it confirmed that the space-time fabric behaves exactly as Einstein's equations describe, even in the extreme gravitational environment around neutron stars. In 2015, the LIGO detectors directly detected gravitational waves for the first time, produced by two black holes spiraling into each other and merging roughly 1.3 billion light-years away. The ripples in space-time, stretching and compressing space as they pass through the detectors, were measured with a precision of less than 1,000th the diameter of a proton. The signal matched general relativity's predictions with breathtaking accuracy. The fabric of space-time is real. It curves around mass, it carries waves, it bends light, slows time, and shapes the paths of everything that moves through it. And every time we measure it, from a Harvard tower to a binary pulsar, to two colliding black holes, it behaves exactly as one theory has said it must since 1915. The neutron star is not an exotic outlier requiring different physics. It is the aircraft clock, turned up to a level where the physics becomes viscerally obvious. Nanoseconds become months, corrections become defining features, whispers become roars, but the voice is the same voice. The mechanism is the same mechanism, and the constant anchoring it all, the speed of light measured identically by every observer in the cosmos, is the same constant it has always been. One mechanism, one fabric, one constant. Every experiment we have discussed tonight, from the interferometer in Cleveland to the atomic clocks on aircraft, from the moons raining through the atmosphere to the gamma rays climbing Jefferson Tower, from the satellites guiding your car to the surface of a neutron star 10,000 light-years away. Every single one of them is a consequence of one physical fact. The speed of light is the same for all observers. That single, stubborn, unbreakable constant demolished Newton's absolute space and absolute time. It forced space and time to become flexible, relative, interdependent. It revealed that the two are not separate features of the universe, but inseparable components of a single, four-dimensional fabric. Space-time, whose geometry determines how clocks tick, how rulers measure, and how objects move. When you walk across a room, you are redirecting a tiny fraction of your fixed space-time speed budget from the time direction to the space direction. Your clock's slow by an amount so small no instrument on Earth could detect it. When a muon streaks through the atmosphere at 99.8% of light speed, nearly its entire budget is spent on spatial motion, and time barely passes for it. Its lifetime stretches by a factor of 20, and it reaches the ground. When an aircraft carries atomic clocks around the world, the combination of its speed and altitude shift the clocks by billionths of a second, exactly as the equations predict. When GPS satellites orbit overhead, the combined velocity and gravitational effects alter their clocks by 38 microseconds per day, and engineers compensate for every one of those microseconds to give you accurate navigation. When light climbs 22.5 meters inside a Harvard tower, it redshifts by exactly the fraction the curvature demands. When an aluminum ion clock sits 33 centimeters higher than its twin, it ticks faster by exactly the amount the geometry requires. And when matter collapses into a neutron star, curving space-time so severely that time on the surface runs a quarter slower than time in the surrounding cosmos, the same equations, the same fabric, the same invariant interval describe the effect with the same precision. These are not separate phenomena that happen to share a family resemblance. They are one phenomenon, one mechanism surfacing in different settings at different intensities. The mechanism is this: because every observer measures light at the same speed, space and time cannot be separately absolute. The only consistent reality is one four-dimensional fabric in which motion through space is purchased with motion through time. That is what it means for space and time to be the same thing. Not a metaphor, not a philosophical position. A measured, verified, continuously confirmed physical fact, written into the geometry of the universe and demonstrated every time a clock ticks. A muon survives, a satellite corrects, or a neutron star bends the flow of time around it. You are embedded in this fabric right now. You are moving through it at the speed of light, as everything in the universe does. Your motion aimed almost entirely in the time direction, because your spatial speed is so small compared to light. Every second, you glide forward through the time dimension of a four-dimensional cosmos, carried by the same geometry that curves around stars and stretches the lives of particles and shifts the frequencies of photons climbing out of gravitational wells. The universe did not have to be this way. There is no logical necessity that demanded space and time be linked. Newton's picture, with its fixed stage and universal clock, is internally consistent. It could have been correct. A universe with absolute space and absolute time is perfectly conceivable. It simply is not the universe we live in. Our universe chose, if that word means anything when applied to the laws of physics, to build itself around one fixed constant, the speed of light, and to let everything else, distance, duration, simultaneity, the shape of space, the flow of time, adjust around that constant in whatever way the geometry requires. The result is a cosmos where space and time are not two things, but one. Where moving faster through space means moving slower through time. Where the presence of mass curves the fabric and alters the rate at which time unfolds. Where the interval between events is the only quantity all observers share. Where the geometry of a neutron star and the drift of a clock on a commercial airline are expressions of the same elegant, austere, experimentally unbreakable truth. You are part of that truth. You are moving through space-time at the speed of light right now as you listen to this. The atoms in your head are aging faster than the atoms in your feet. The flow of time around you is shaped by the mass of the planet beneath you. And every photon that reaches your eyes from a distant star has crossed a fabric that bends and flexes and trades space for time, and time for space, all to preserve one constant that the universe will not surrender under any circumstances. Space and time are not two different things. They are one fabric, one geometry, one reality, and every clock that has ever ticked, every particle that has ever decayed, every signal that has ever crossed the void between satellites and the ground confirms it. That is not a belief. That is a measurement. And it is a measurement you participate in every moment of your life, whether you know it or not. The space-time fabric does not wait for your awareness. It does not require your understanding. It operates on the atoms of your body, the light entering your eyes, the signals crossing your phone, the satellites wheeling overhead, with perfect indifference to whether you grasp what is happening. The universe applies its geometry to everything equally. Your comprehension is not required. Only your existence within the fabric is necessary, and that you cannot avoid. But there is something remarkable about the fact that you can comprehend it. The fabric of space-time has been curving light and slowing clocks since the first moments after the universe began, billions of years before any mind existed to wonder about it. Stars formed, burned, exploded, and scattered their atoms across space, all moving through a four-dimensional geometry none of them could contemplate. Planets coalesced from dust and gas and orbited their stars along geodesics they could not name. And then, on at least one small planet, matter organized itself into structures complicated enough to notice what was happening, complicated enough to measure it, complicated enough to write equations that describe the curvature of the cosmos with precision better than 1 part in 100,000. You are made of atoms forged inside stars that move through the same space-time fabric you are moving through right now. The iron in your blood was created in the core of a star that exploded before the sun existed, and the light from that explosion was gravitationally redshifted as it climbed away from the debris, stretched by the same curvature that Pound and Repke measured in a brick tower. The calcium in your bones was assembled in stellar furnaces where time ran at a different rate than it does here on the surface of Earth, because those furnaces sat in deeper gravitational wells with more severely curved space-time. You are, in a very literal sense, a structure made of space-time history. Every atom in your body has traveled through curved geometry for billions of years to arrive at the precise location and the precise moment where it became part of you. And now, assembled from ancient stardust, sitting on a planet whose mass curves the fabric beneath your feet, aging faster at the top of your body than at the bottom, you understand why. Not because someone told you to believe it, because the clocks proved it, because the muons proved it, because the satellites prove it every second, because a brick tower at Harvard and an aluminum ion in Colorado, and the crushed remains of a dead star 10,000 light years away all tell exactly the same story in exactly the same mathematical language. Space and time are one thing. They always have been, and now you know.